Now you have been able to understand how the integration by part formula came about in my previous video, which was derived over here. Now, that obtained equation or formula over here can be used as a formula for integrating in certain situations, which is some situation in which the integrand or the question being given is a product of two functions, as I explained over here using this function, right? Using this function. And one of these functions can be integrated using techniques that we have already developed. So let's straight away use some simple example to illustrate that. Using the integral of x multiplying by exponent x with respect to dx. As you can see over here, this function as one function, which is maybe y equal to x multiplied by exponent x, is a product of two functions, which is x and then exponent x. And therefore we can consider it as integral of x into bracket exponent x dx. Which is equal to integral of u dv. So in this case, our u is x and our dv is what? Exponent x. That is if I am choosing exponent x to be my dv. But if you choose that your exponent x should be here and then your x should be the x over here, it means that your u is going to be this and your dv is going to be this. But remember that in integration by parts, we choose the one to be our dv if it can be integrated, and then we choose u to be our u if it can be differentiated, and we choose it in such a way that as time goes on, it will make the original function as simple as possible for us to solve, but not rather increasing the complexity. So in this case, we can say that if, assuming we are making x exponent x dx over here, we can say that our u equal to x and then our dv equal to exponent x dx, as I was explaining over here. Now in this case, let's see what we can do. As I told you earlier on, when you have u equal to x, then you need to know what component are you looking for. Now you have this, you have this. What are the components are you looking for? And you will be able to know the component that you are looking for after being able to assign the dv and the u for the functions by bringing out the integration by parts formula. That's why I said this formula must be on your fingertips. And this is the formula, which is the integral of u dv, which is equal to uv minus the integral of v du. So in this case, we have been able to assign our dv and our u over here. And now what are we going to do again? Now, if you look at the formula, we can see that we have our u and we have our v, and we have our v and we have our du. But when you look at whatever we are having here, we have only our u and we have only our dv, which is dv here, our dv here, and then our u here, and we also have u here. We don't have v, we don't have du. So in finding the u, you need to go to find the differential of u with respect to x, and differential of u with respect to x here, it's 1. That is the u dx is equal to what? 1. So making the u the subject, we are going to get the u is equal to, because I'll multiply both sides by dx, both sides by dx is equal to dx. That's 1 times dx, which is the same as dx. Now I have my du is equal to my dx. That is what I have over here. What do we want to get again? Now we have our du, but we don't have our v. Right? We don't have our v, but we have dv. And if we want a v from a dv, what do? We integrate. So when we integrate, what are we going to get? So that means the integral from both sides, and now we are going to get our v equal to the integral of exponent x. We are going to get exponent x again. Now, bringing into your attention, I have my v. I have my du, which is here. I have my u, and I have my dv. So now you can see that I have dv, I have u, I have v, and I have du. So now it means I am good to go. And from here, someone may ask, why is it that after integrating this, we didn't bring the integration constant? But keep in mind that integration by parts, we select c to be 0 to obtain the simplest antiderivative form. So based on this, now you know the formula, that is the formula, so let's put it inside. So let's take the formula here so that it will be easier for us to do it. So the formula is integral of u dv, which is equal to uv minus integral of v du. Now let's write them over there. Where is our u? Our u is x. Now integral of x. Then where is our dv? Our dv is exponent x dx. Is this not the same as the question being given, which is this? Is the same, which is equal to. So where is our u? We calculated for our u, or our u is already here, is in the question, which is what? X. Where is our v? We calculated for our v, which is exponent x. So this is the separate term. And now minus, what are we looking for again? Our v. Where is our v? Our v is exponent x. Now integral of exponent x. Where is our du? Our du, it's what? 1, which is 1 times dx, which is what? Dx. So as I said earlier on, through integration by parts, we have been able to transform this function into a term, and a simplest term which can be easily for us to what? Integrated, which makes, in terms of makes integration by part formula very, very useful. So in view of this, we all agree that we can just close our eyes and then integrate this exponent x with respect to x, and you will be good to go. So in doing that, you are going to get your final answer to be x multiplied by exponent x minus integral of exponent x is the same as exponent x. And then don't forget that this is your indefinite integral, therefore you need to bring your plus c. So the only difference between the one that I was explaining here, saying that we need to assign c to equal to 0, is that when we are assigning the dv and the u, and then we need to find our v, and when you integrate to find our v, we don't add the c. We assume that c equal to 0 to make or to obtain the simplest antiderivative. But when you are done integrating and the resultant one, there's no limits assigned to it, you need to bring your constant of integrating, which is what? C. So this is our final answer for this question. So you can see that per what we have done here, mostly we choose u for a function or a function in the question that can reduce that particular function into the simplest form. For example, if we assign u equal to exponent x over here, the du dx is still going to give us exponent x, which is not reducing. But when we assign u equal to x, du dx of this x is equal to 1, which is in terms of reducing it. Let's assume that our u equal to x squared. Du dx is equal to 2x, which has reduced the power to 1. And when we do the integral again, we are going to get 2, which has reduced the x power to 0. So one trick that you have noticed here is that most of the times, do well to assign u to the function that can reduce or that can be reduced to its simplest form. And we will come to that. So this method of integration is called integration by parts. And as we always do, we can simply differentiate whatever we get to see whether we are going to get our original function back. And we should be aware that the integration by parts, like substitution, is a trial and most of the times error processes. Sometimes when you assign the u and then the v, and you see that the problem is becoming very, very difficult or complex, you need to stop wherever you are and come and reassign the u and the v so that things will be easy for you to go. But I know that, or I'm sure that before we end the whole tutorial about integration by part, you'll be able to know when to apply integration by part and when not to apply, or what to assign u for and what to assign the v for. So in this case, let's look at something here. As I was explaining earlier on, assuming that we assigned our u equal to exponent x and we assign our dv equal to x dx, our du is going to be exponent x dx again, because we find it will be, or let me not jump straight away. Let's say something here. Our du dx equal to exponent x, of which when we simplify it, we are going to get du equal to exponent x dx. Now, based on whatever we have signed here, our v will come from integral of dv, which will give us x squared over 2. That's integral of x. Now you can see that here the function is rather increasing instead of decreasing, which sometimes will make our function become complex to integrate. So assigning it or substituting it into the formula, we are going to get integral of exponent x and then x dx is equal to, when we substitute the u, we are going to get exponent x. When we substitute the v, which is the term in the formula over here, we are going to get our x squared over 2. And then minus the integral of x squared over 2 exponent x dx. So you can see that the separate term which need to be further integrated is even becoming harder or complex than the original question which was given. So now the integrand on the right is more even difficult to integrate than the one with which we began with, as I am currently stating. So when we can integrate both factors of an integrand and thus have a choice as to how to apply the integration by parts formula, it can happen that only one of the possibilities will work. But sometimes, if you are lucky, the two can work, but just that will make your work more difficult if you don't choose the right, or you don't make the right decision for the chosen of u and then v. So to conclude on this tutorial, and then we come on in solving more examples on this, I would like to give you some tips on how to use integration by parts. So the first one is that when you are given the question and you look at it, or you do some visual inspection and you see that you can't use substitution for this, then try integration by parts. But before this video will go to an end, or this tutorial on integration by parts will go to an end, you will get to know when to apply integration by parts and when to apply substitution method. But some books will tell you that if you have no success using integration or substitution, just try integration by parts. So the second one that I will tell you is that the integration by parts formula is being applied when the integration is in the form f of x multiplied by g of x dx. And when you get something like it, means that it's a function, two functions being multiplied together. It can be x and exponent function, or polynomial function and exponential function. It can be an exponential function and trigonometric function multiplying together. It can be a trigonometric function and polynomial function multiplying together. It can be even exponential function and a variable, like what we did earlier on, multiplying together. And in view of this, you should be able to match the example given to you in the form of integral of u dv, so that you'll be able to choose your u and you'll be able to choose your dv to kind of make your work simpler for you to solve. And as I said earlier on, there are two functions multiplying together, and when you see that, sometimes substitution may help, but if you get no success in that, or when you do visual inspections and you are not able to solve that, then you come to integration by parts. And you should be able to match it like this: integral of u dv. So by choosing a function to be maybe your u, assuming that you are choosing your f of x to equal to be your u, and maybe your dv to be your, or let's say dv to be your g of x, it means that your f of x can be differentiated. This f of x can be differentiated, and my observation, or the observation that I've been doing, is that the one that mostly you choose for the u, when you differentiate it, especially when it is polynomial, it must decrease the degree of the polynomial. And then dv must also be integrated, right? So the next one is to find your du, but this one, mostly I don't ask students to just chew it. What I tell them to do is that, first of all, when you get a question and you get to know that you are supposed to use integration by parts, the only thing that you need to do is to write down your formula, which is integral of u dv, which is equal to vu minus the integral of v du. And from there, when you are able to match the function here in the form of this, look at whatever is here or the variable that you don't have from the matching and calculate for them. And from there, when you have your dv, you can see that per integration you can get your v from it. When you have your u, you can see that per du dx, you can get your du from it. And then the rest is to do substitution into the formula. So I will simply say that find your du by differentiating what? Differentiating your v. By differentiating your u, and then find your v by integrating what? Your dv. As simple as that. So if your original resulting integral is more complicated, right? As we did earlier over here, we saw that even this additional term, this separate integral, it's even becoming more complex than whatever was given to us earlier on. This means that we should make some other choices for what we choose for our dv and what our u. That's very important. So when we are able to do that, things will be smooth for us and we'll be able to solve for the integration. After that, whatever result that you get, if it is indefinite integral, just add your c. If it's definite, just put in upper limit minus lower limit for, as we do always, and from there you will get your answer. When you get your answer, as you always do, check your result whether you are correct or not by differentiating the result to see whether you are going to get your original function back. That will depend on you. So thank you for watching and see you in my next